Okay, this is problem set 15, where we start talking about chemical names and formulas and the nomenclature that we use in order to identify different molecules. So the first thing I'm going to do here is I'm going to go through the rules for naming chemical compounds, and then it'll just be a matter of applying it throughout this problem set. So I'm just going to jump over here, and we're going to talk about the rules. So first, I'm going to talk about covalent, because the rules are different if you're talking about a covalent compound and an ionic compound. So if you're curious about the difference between covalent and ionic, watch my video for problem set 14 where we talk about bonding. So covalent, if I have a covalent compound, two nonmetals, then I'm just going to give two examples here. So H2O and CO2. So H2O, it's just water, right? But the nerdy name, the official name would be dihydrogen monoxide. Monoxide. And then CO2 we know as carbon dioxide. Okay, so in these two molecules we have all the information we need about covalent naming. So the rules are you have your two elements and you give prefixes to tell how many of each element you have. So here I have two hydrogens, so dihydrogen, and one oxygen, so monooxide or monoxide. You can see that's different here though, right? We got CO2, we only have one carbon, and we don't say monocarbon, and that's because the assumption is that if there's no prefix on the first thing, then there's only one of that thing. So I can just say carbon, which means one carbon, and then dioxide because there's two oxygens, and you do notice that you put the "ide" at the end there as a matter of convention. So the prefixes you should know, we've got mono, di, tri, tetra, pentas 5, hexa, hepta, octa, or octo, I don't know, and then non, dec. Okay, so you see that all of these have vowels at the end of them. That's in case, like, if you're labeling something that starts with the consonant, so I need a value. So like decacarbon, right, or nonacarbon. But if I'm labeling something that starts with a vowel, like oxide, like here you can see monoxide. Sometimes we just take the vowel at the end of the prefix and replace it, or just kick it out, and you just use the vowel. Really, just whatever kind of sounds natural is a good rule for how you use those prefixes. Alright, so that's how you name covalent things. Now ionic. Ionic is a little bit more complicated. Well, or it could be simpler depending on the way you think about it. If I have NaCl, okay, that's a sodium ion with a chloride ion. So we call it sodium chloride. Okay, now that probably seems simpler than having to say sodium monochloride like you would if it was covalent. And the reason we can just say sodium chloride is because we know, based on the periodic table, if I look at the periodic table, sodium is here. Sodium, if it's going to form an ion, loses an electron so that it has an electron configuration similar to neon. Chlorine, on the other hand, gains one to have electron configuration similar to argon. As a result, sodium always forms a +1, chlorine always forms a -1, and we just need to combine these two ions in whichever ratio gives a neutral charge. Well, if I have a +1 and I stick a -1 on it, what happens to the charge? Those cancel out. That's neutral. And so because I know that these charges are always going to be +1 or -1, I know that just by saying sodium chloride, I'm going to have one sodium and one chlorine. Now that's not the case over here, because here I'm not using ions to determine how many of each thing, right? So for example, carbon monoxide and carbon dioxide are both things, right? And so that's why I need you to say carbon monoxide to tell me there's one oxygen, or dioxide to tell me there's two. With ions, that's not the case. So let's just do another example. If I were to say magnesium chloride. Well, I know that I'm going to have a magnesium, and I know that I'm going to have a chloride, but I need to know how many of each. Well, if I look at the periodic table, magnesium forms a +2, chlorine forms a 1-. So if I have magnesium 2+, chlorine 1-, how many of each do I need to be neutral? Well, 1 magnesium and 2 chlorines, because if I have a 2+ and I have 2 1-, that balances out to neutral. So magnesium chloride. All right, so what if, here's one variation, I guess, one additional rule to know. If I were to say iron oxide, be Fe with an O, and I'd say, all right, oxygen forms a 2-. Fe forms, don't know, because in reality, with a lot of these transition metals, they can form multiple cations. And like iron, for example, can form a 2+ or a 3+, and that's hard to know just from the periodic table, and that's true with pretty much all the transition metals. So as a result, it's not enough to say iron oxide because I don't know what the charges are, and so I can't figure out what the ratio is. And so what I need is something like this. So in order to circumvent that issue with transition metals and really anything that can form multiple charges, but typically we just care about transition metals, is you need to give the charge of the transition metal in Roman numerals. So here I know that this iron that I care about in this molecule is an Fe2+. The oxygen forms a 2-, so those balance already, so the answer is FeO for iron 2 oxide. But what if I had iron 3 oxide? Still iron, still oxygen, Fe3+, O2-. How am I going to balance these out? Well, I can't do 1 and 1, because then I'd have a 3+ and 2-. That wouldn't be balanced. And so what I end up doing is if I have 2 of those, that's a 6+. And if I have 3 of those, that's a 6-. Those balance, so I need Fe2O3. So you can see here, as a result of iron being able to form multiple charges, we end up with an iron 2 oxide and an iron 3 oxide that are different molecules. And so that's why with transition metals in particular, you need to put the charge of the metal in Roman numerals there. All right, the last thing to talk about with ionic compounds is something called polyatomic ions. Polyatomic ions. So just think about the name. Poly means multiple, atomic, multiple atoms making an ion. So up here, O2-, that is a monatomic ion. That's one atom that has a charge. Okay, so polyatomic ions is multiple atoms that have a charge. So let me pull up a list of some common polyatomic ions. All right, so here we have a list of some common polyatomic ions to know. So, for example, NO2-. So that N and those two oxygens are covalently bonded. They're a molecule. They're bonded to each other, and together they have a -1 charge. Well, that's a polyatomic ion, multiple atoms making an ion, and it's called nitrite. NO3- is called nitrate. Okay, so there's not a real good way, not a real good pattern for learning these names, but at least for Chem 105, you'll need, these are the ones that you'll want to be able to identify from memory. So let's say, for example, I had this nitrite, NO2-. What if I had, whoa, there we go. What if I had potassium, did I spell that right? 2 S's. Potassium nitrite. Well, I know that potassium is a K plus and nitrite is an NO2 minus. So how many of each do I need to be neutral? Well, 1, so just KNO3. But what if I had magnesium nitrite? Magnesium is Mg2 plus. I've got an NO2 minus, which means I need 2 nitrites to balance 1 magnesium. And so it would be Mg, and then in parentheses, NO3, and I need 2 of them. Okay? So that's how we would deal with polyatomic ions. So now that we've had this crash course on naming covalent and ionic compounds, let's do some. Write the chemical formula and name the ionic compound formed by the following elements. All right, calcium, and I'm actually going to pull up my periodic table. Calcium, Ca2 plus, sulfur 2 minus, so that's going to be CaS, and it's going to be called calcium sulfide. Sulfide. Okay, lithium. Lithium forms a plus, chlorine forms a minus, so LiCl. Lithium chloride. We then have magnesium 2 plus, fluorine minus, so you can't necessarily see all the minuses. Fluorine forms a 1 minus. Okay, and so that means for each 2 plus from the magnesium, I'm going to need 2 fluorines. But that doesn't matter, I still just call it magnesium fluoride. Calcium again is a 2 plus, oxygen is a 2 minus, so just get CaO, calcium oxide. Hopefully you recognize these are all ionic compounds. So I'm looking at the charge. Aluminum 3 plus, oxygen 2 minus, so to balance that, I'm going to need Al2O3 for aluminum oxide. Rubidium is down here, forms a 1 plus, nitrogen forms a 3 minus, which leaves me with Rb3n, which would be called rubidium nitride. Alright, iron 3 and oxygen. That 3 tells you it's a 3 plus, and oxygen 2 minus. That's going to give me Fe2O3, which we call iron 3 oxide. And then we've got cobalt 2 plus, chlorine minus, and then 6 waters of hydration. We didn't talk about that, but I'll be able to show you in this problem. So we need, for 1 cobalt 2 plus, we need 2 chlorine minuses, so whatever, not worried about that, just ignore that. Cl minus, so I'm going to have cobalt Cl2, and then for the 6 waters of hydration, you just put a big dot and put 6H2O, and then the way we call that would be cobalt 2 oxide, and then you add, because there's 6 waters, hexahydrate, in case you ever see something like that again. Alright, that brings us to number 2, where we're just naming polyatomic ions. Now, you will want to have these polyatomic ions memorized, but for the sake of this homework assignment, there's not like a skill or a way to learn how to name them, so looking them up is as good a way as any. So here I have them, have some of them, so not all. Oh, there's phosphate, so this is phosphate, CO3 2 minus is carbonate, sulfate, hydrogen sulfate, perchlorate. This is hydrogen carbonate. You'll also see it called bicarbonate. And the 3 minus nitrate. We got hypochlorite. And H4 plus is ammonium. Then we have nitrite, acetate to C. You'll also see this labeled CH3CO. O minus is another way to write acetate. You'll often see. That brings us over here. Hydroxide is OH minus, cyanide is CN minus, ClO2 minus for chlorite, and ClO3 minus for chlorate. Acetate again, CH3COO minus is the more common way to write it. Permanganate, MnO4 minus. Chromate is CrO4 2 minus. Dichromate, C2O7 2 minus. Thiocyanate, SCN minus. Bicarbonate, HCO3 minus, and azide is an N3 minus. Again, if you're in BYU's Chem 105 class, you really care about these ones that are on this table, which is available online. Alright. There we go. Alright, and we want to write the chemical formula for the following compounds. I'm going to jump back over to my periodic table. This is doing the same thing we did in number 1, but in the opposite direction. So, sodium nitrate, and we have some polyatomic ions. So sodium Na plus, nitrate NO3 minus, so it's going to be NaNO3. And then we get copper 2, sulfate, that is SO4 2 minus, and then pentahydrate, so that's going to be, we just need one of each to balance. Alright, magnesium is going to be Mg2 plus, perchlorate is ClO4, I could probably jump over here, perchlorate, ClO4 minus, which means we're going to need 2 of those for each magnesium to be neutral. Alright, hydrocyanic acid. Let me see the rest of this, because we didn't talk about naming acids, but maybe I'll take the opportunity right now to do a little brief thing about how to name acids. So we have covalent, we have ionic, and then let's do acids. So there's 2 types of acids. There's binary and there's oxo. Binary means that you have a hydrogen, an H plus, that gets stuck onto an anion. So if I had like F minus, that would make HF, and we call that hydrofluoric acid. So we add hydro, then we say whatever this is, ic acid. Okay, so we usually just see this with halides. So HCl is hydrochloric acid. We get HBr for hydrobromic, HI for hydroiodic. And that's binary acids. Binary because it's just like a hydrogen and one other thing. That brings us to oxo acids, which is taking H pluses and sticking them onto polyatomic ions. So let's say that I had an H plus and I stuck it on nitrite. I would get HNO2. I could also take H plus and stick it on nitrate, and that would give me HNO2. 3. Okay, so how do we name these? You look at the polyatomic ion that this acid contains, so in this case nitrate, and if it ends, nitrite, if it ends in an ite, it turns to OUS, acid. Nitrite turns to nitrous acid. Nitrate turns to nitric acid. Okay. Now, like HCl is hydrochloric acid, so this is also ic acid, but you have the hydro up front in a binary acid. That's how you name acids. These are called oxoacids because the polyatomic ions have oxygen in them. There is one, however, that does not, that we really care about, and that's Cn-. So if I have an H plus and I stick a Cn-, Cn- on it, I get HCN because there's no oxygen in that polyatomic ion. It follows the binary acid rules, and so it would become hydrocyanic acid. And if you remember well, that's right here, hydrocyanic acid. And so that's cyanide with a hydrogen on it, HCN. All right, let's keep going. We have ammonium bisulfate. So ammonium is one of the polyatomic ions, NH4+. I'll jump that back over here. Ammonium is right there, NH4+. Bisulfate is the same as hydrogen sulfate right there, so HSO4-. Now you might be wondering, why is that not the acid? Because if I had SO4 2-, if I wanted to turn that in, so that's sulfate, if I wanted to turn it into sulfuric acid, I would need to add 2 hydrogens. H2SO4, that would be sulfuric acid, but with only adding 1, you haven't neutralized the charge yet, and so it's not the acid name. So how many of each of these do I need? Just 1 of each to be balanced, so I get NH4HSO4. Alright, lead, Pb, and they say 4+, plus phosphate. Phosphate is PO4 3-. Okay, so in order to balance those, I'm going to need 3 leads and 4 phosphates. Alright, sulfurous acid. So that brings us back to acid. So this is OUS, which means it should be IC. So we have it should be ITE. It should be an ite if we go to us. And so sulfite is what we're looking for. And sulfite is SO3 2-. And so then we want to make it an acid. We got to replace those 2 charges with 2 hydrogens. So that would be sulfurous acid. All right, what are the names for the following compounds? We're doing the same thing but opposite. So CO3, that is carbonate and nickel. So this is nickel carbonate. Okay, but if remember, nickel is here in the transition metals, and so we need to give it its charge. How do I figure out its charge? Well, I know carbonate is CO3 2-. So if there's only 1 nickel with that 2- carbonate, this must be 2+. So nickel 2 carbonate. All right, Cn- is, wow, it's not even on this. Oh, there it is, cyanide. So this is sodium. Cyanide. This would be lithium, and it's got a bicarbonate on it. Calcium. And what's the polyatomic ion? ClO. This can be ClO1-. Right there. Hypochlorite. So hopefully you recognize that using these polyatomic ions, you still name it the same way. You just say the name of your cation and the name of your anion. It's just that your anion has a special name because it's a polyatomic anion. All right. magnesium. ClO4 minus is perchlorate. NH4 plus is ammonium. And NO3 minus is nitrate. You might also be wondering, how do I know it's NH4 plus? There's no plus there. That's really just recognition. I know that I can tell I know NO3 minus is a polyatomic ion and NH4 plus is a polyatomic ion, so this is going to be an ionic compound between those two polyatomic ions. Okay, I've got copper, and I have acetate. Okay, but I need the charge on the copper because it's a transition metal, and so I know that acetate is 1 minus, and so there's 2 of them, which means this copper must be a 2 plus to need 2 acetates. All right. More than half a dozen neutral compounds containing, I can make this full screen now, containing only nitrogen and oxygen are known, and more than half a dozen neutral compounds containing sulfur and oxygen are known. What are the names or formulas of the compounds? Names or formulas of the compounds given below. They give us the formulas, so we're going to give the names. Hopefully you recognize these are covalent compounds because nitrogen and oxygen are both nonmetals. Sulfur and oxygen are both nonmetals. Oh, that's why it says or formulas, because we'll get the formulas down here. And so with these, we just need to put prefixes on every atom, unless it is the first atom and there's one of them. So in this case, this is just nitrogen trioxide. I don't need to put mono because it's assumed that the first one is 1. Dinitrogen pentoxide. Dinitrogen tetroxide. Nitrogen dioxide. Now you might be wondering, no, I thought that was nitrite from the table of polyatomic ions. It would be nitrite if it had a negative on it, but it doesn't, so it's just nitrogen dioxide. It's not a polyatomic ion. Dinitrogen trioxide. Nitrogen monoxide. Dinitrogen monoxide. We have tetranitrogen monoxide. Awesome. Now we go down here. Let's go the other direction. So sulfur monoxide, sulfur dioxide, sulfur trioxide, disulfur monoxide, and hexasulfur monoxide, heptasulfur dioxide. So hopefully covalent comes a little bit easier maybe than ionic does. All right, last one. Potassium nitrate has many uses. It was used as a preservative in salted meat until very recently. It is a major constituent of gunpowder, fireworks, solid rocket propellant, but perhaps its current most widespread use is a source of fixed nitrogen in fertilizer and tree stump removers. How many grams of nitrogen are found in 50 grams of potassium nitrate? That's the real question. Hopefully potassium nitrate is going to be KNO3. So there's kind of 2 ways to solve this problem. I'm going to solve it both ways. So we know that our starting amount is 50 grams of potassium nitrate. And we could calculate from the periodic table that 1 mole of potassium nitrate weighs 101.1 grams. And then I can say, I don't really care about potassium nitrate. What do I care about? I care about nitrogen. Well, I know, since I'm in moles of potassium nitrate, I know that 1 mole of potassium nitrate has 1 mole of nitrogen in it. Why? Because this N has a 1 nitrogen. So if I was going to oxygen, this would be 3 moles of oxygen and 1 mole of potassium nitrate. And then I can say I know 1 mole of nitrogen has 14 grams of nitrogen. I can plug that into my calculator, and I get about 6.92 grams of nitrogen. The other way to solve this problem is to figure out what percent of the mass of potassium nitrate is nitrogen. So to do that, I would say how many grams of nitrogen in grams of KNO3. Well, since there's 1 atom of nitrogen, so 14 grams of nitrogen over KNO3 is 101 grams, which tells me, let's do this, so percent nitrogen, which tells me that potassium nitrate is 13.85% nitrogen. And then I could just say, well, I know I have 50 grams of potassium nitrate times my percent that is nitrogen, and I get 6.92 grams of nitrogen. So same answer, different method. Really, if you think about the math you're doing, it actually is the same, because this is just 50 times 14 over 101.1. This is 50 times 14 divided by 101.1. So nothing really fancy there other than 2 different kind of ways to think about the problem. So there we go. There's our introduction to how to name chemical formulas and then derive chemical formulas from chemical names.